in the first proof, we are proving that G is the midpoint of EF. In order for G to be the midpoint of EF, it would need to split EF into two equal parts. So basically, we need to prove that EG is congruent to FG. So EG and GF are sides of these two triangles. So what we need to do is we need to prove those two triangles congruent. And then once we know that they're congruent, we can use CP/CTC to say that EG is congruent to FG because CP/CTC stands for corresponding parts of congruent triangles are congruent. And once we have proven that triangles are congruent, that means everything else about them is also congruent, all of their corresponding sides and all of their corresponding angles. So now that we have that plan, let's mark the diagram with the givens and let's see how we can prove the two triangles congruent. And I'm gonna just highlight again those two triangles that were proven congruent so we can focus on them. Okay. So in the givens, we have that AB is congruent to CD, and we have that AB is parallel to CD. We also know that DE is congruent to BF. Let me make my statement reason chart, so that way as we come up with something, I can record it. And let me give myself a little bit more space. There we go. I'm not going to write the givens down for this video because it'll just take extra time and space here, but I'm going to make a spot for the givens. From the givens, I can say that ABCD is a parallelogram. And that's because one way of proving that we have a parallelogram is if one pair of opposite sides are both congruent and parallel. If one pair is both, then it's a parallelogram. If one pair of congruent sides are both congruent and parallel, the quadrilateral is a parallelogram. So from here, now that we know that it's a parallelogram, we can say that AD and BC, the other set of opposite sides, are also parallel. And that's because opposite sides of a parallelogram are parallel, and we now know that we have a parallelogram, we just proved it. And from there, I do have a letter Z, which you might have noticed. So I can say that the alternate interior angles are congruent because now I have parallel lines. So angle DAC is congruent to angle BCA. Alternate interior angles are congruent when lines are parallel. You might have noticed that we also have congruent vertical angles. Angle AGE is congruent to angle FGC because intersecting lines, anytime you have that letter X, those intersecting lines, they form congruent vertical angles. So now we have two A's, but angle proves similarity. It doesn't prove congruence. So we do need a side. All of our congruence methods, I'm going to just write them here so we can refer to them. They all involve a side. So we do need the side. We have two A's already, so it's either going to be ASA or AAS, depending on where we can get the side. And where the side's going to come from is from our givens, because they already gave us information about BF being congruent to ED. Sorry, DE being congruent to BF. And since we do have a parallelogram, not only are opposite sides AD and BC parallel, but AD and BC are also congruent. So what we can do is if we start with AD and we subtract off DE, we get rid of DE, we'll be left over with AE, which is a side of the triangle that we want. And if we start with BC and we subtract off BF, then we'll be left with FC, which is the side of the triangle that we want. This is subtraction. And then in step 8, we're just saying if we do AD minus DE, we get AE. If we do BC minus BF, we get FC. We're just replacing the subtraction with what it's equivalent to. And that's substitution. And from here, we now have in our triangles angle, angle, side, angle, angle, side. 2 angles followed by a side. So I could now say triangle AEG is congruent to triangle FCG by angle, angle, side. And now, like we spoke about at the beginning of this video, since the triangles are congruent, we can now say that EG is congruent to FG. Because once the triangles are congruent, all the other stuff about them, all the corresponding sides, all the corresponding angles are automatically congruent. And that's CPCTC. And from here, we have everything we need to say that G is the midpoint of EF because a midpoint splits a line segment in 2 congruent parts. And that's what we just showed is happening. We just proved that EF is being split into 2 congruent parts, EG congruent to FG. And we're all finished. In the next one, if we take a look at the proof statement, we're proving that FG is congruent to EG. FG is the side of this triangle, and EG is the side of this triangle. So those are the 2 triangles that I need to prove congruent. And once I prove the triangles congruent, then I'll know that EG and GF are congruent because they're corresponding sides of the triangles. And as we spoke about in the last example, once triangles are congruent, all of their corresponding sides and angles automatically are congruent by CPCTC. So now we have our plan. Let me just re-highlight these so we can see which triangles we're focusing on so that we can make sure that the information we're using is going to be helpful to those 2 triangles. And let me start my statement reason chart. Just like in the last one, I'm not going to write down my givens because I don't want to take time and space in this video. And let's read the information and mark it. We know that angle ABG is congruent to angle CDG. We know that AB is congruent to CD. And we know that CE is congruent to AF. The 2 angles that they give us form a letter Z. So they're alternate interior angles. And if we have congruent alternate interior angles, that proves that the lines forming them are parallel. So we can say that AB is parallel to CD. I'm going to write that down. AB is parallel to CD if alternate interior angles are congruent, lines are parallel. Now from here, I know that ABCD is a parallelogram because just like in the last example, if one pair of opposite sides is both congruent and parallel, it's a parallelogram. ABCD is a parallelogram. If one pair of opposite sides are both congruent and parallel, it is a parallelogram. The quadrilateral is a parallelogram. From here, I can say that BC is parallel to AD because now I know it's a parallelogram. And I know that opposite sides of a parallelogram are parallel. And then, since I have parallel lines, I can use the alternate interior angles that will help me that are inside the triangles that we want. Angle BEG congruent to angle DFG. Alternate interior angles are congruent when lines are parallel. We can also say, since it's a parallelogram, that BC is congruent to AD. And now, similar to what we did in the last example, if we start with BC and we subtract off EC, we'll be left over with BE, which is a side of one of the triangles that we're interested in. And if we start with AD, and from that we subtract off AF, we'll be left with FD, which is a side of the triangle that we're interested in. So we can say subtraction followed by substitution, just like in the last example. And already we have an angle and a side in our two triangles. And just like the last example, we also have congruent vertical angles. So I can say angle BGE is congruent to angle FGD because intersecting lines form congruent vertical angles. And just like in the last example, we now have angle, angle, side. We have angle, angle, side. I'm going to just continue up here with step 10. We have triangle BEG congruent to triangle DFG. And that's by angle, angle, side. And then from here, just like we talked about at the beginning, I'll use a different color for this actually. We can say that FG is congruent to EG, BCTC. We already proved the triangle is congruent. And CPCTC allows us to say once the triangles are congruent, everything else is also congruent. All of the corresponding sides and all of the corresponding angles are also congruent. For this one over here, first we need to figure out which two triangles we're focusing on. I'm going to use my proof statement for that. TA, HA, HE, TH. So the two triangles I'm focusing on are the two big triangles, these two large triangles here. from the proof statement. And I see that we're proving a product. There's multiplication in the proof statement. So since we're proving a product, products come from proportions and proportions come from similar triangles. So this is going to be a similar triangle proof, and it's going to be 3 steps. The steps are going to be 1, prove the triangle similar. And anytime you're doing a 2-column proof with similar triangles, it's always going to be by AA. We don't have numbers, so we can't show proportional sides. Then we're going to prove our proportion involving the segments from the proof statement. And finally, we're going to prove the product that we are actually interested in proving. So let me write my statement reason chart. I'm not going to write the givens, just like the other ones, and we can get started. So we're looking for angles. They tell us that HM is congruent to AT. And they tell us that HT is congruent to AM. So already, I know that we have a parallelogram. And I know that because if both pairs of opposite sides are congruent, then the quadrilateral is a parallelogram. And now I can say that HT is parallel to MA. Since it's a parallelogram, I know that opposite sides of a parallelogram are parallel. And that can help me get my alternate interior angles. Notice how a lot of the proofs use alternate interior angles. Angle THA is congruent to angle EAH. Alternate interior angles are congruent when lines are parallel. And then from here, we still have more givens to use. HE is perpendicular to MEA. That means it forms a right angle. And HA is perpendicular to AT. So where they intersect, they also form a right angle. And that gives us our second A for AA. Let's get this into our proof. Angle TAH and angle HEA are right angles because perpendicular lines form right angles. And since we're going to be using them for AA, we do need to say they're congruent to each other. The 2 angles are congruent due to AA. Oh, sorry, are similar due to AA. I almost messed that up. Oh, no. Oops. I'm jumping ahead here. The 2 right angles are congruent because all right angles are congruent. I'm jumping ahead. In my mind, I thought I was up to proving the triangle similar. Now I'm saying the right angles are congruent. Right angles are congruent because all right angles are congruent. They all measure 90 degrees. From here, this is where I was jumping ahead to. I can say that the 2 triangles are similar. Triangle HAT is similar to triangle HEA, and that's by AA, following our plan from the beginning. And now, following our plan from the beginning, we can prove a proportion involving the segments from the proof statement. When you put the segments from the proof statement into your proportion, just double check that they cross multiply to give you the proof statement. I'm going to double check that right now. I'm going to put step 9 down here. When I cross multiply, I get TA times HA. So far, so good. HE times TH. Always double check. It's very easy to mess that up. When you're proving a proportion, it's the same reason every time. It comes from the similar triangles. Since we've proven that the triangles are similar, we know that corresponding sides of similar triangles are proportional. And then for the product. We get from the proportion to the product by cross multiplying, but you can't write cross multiplying on the Regents exam. The fancy way of saying cross multiplication is in a proportion, the product of the means equals the product of the extremes. And there we have it, the full proof. Okay. For this one, we need to prove that ABCD is a rhombus. A rhombus is a special parallelogram that has extra special properties. The three special properties of a rhombus are all sides are equal. And remember, if you already know you have a parallelogram, you don't actually have to show all the sides are equal. As long as two adjacent sides are equal, two consecutive sides are equal, that's enough to prove it's a rhombus. And since it's already a parallelogram, the opposite sides are congruent, so that means all the sides are equal. So all you have to do is show that two consecutive sides are equal to make it a rhombus. The other two special properties are about the diagonals. Diagonals are perpendicular and diagonals bisect the angles, but we don't have any diagonals here. So the way that we're going to prove that it's a rhombus is by showing consecutive sides are congruent. And the two consecutive sides that are sides of triangles are BC and CD, and we're always looking for triangles. So if I can prove these two overlapping triangles congruent to each other, then I can CP, BC, and CD, and then I can have that it's a rhombus. When you have overlapping triangles, redraw your triangles. I'm going to try to redraw them as best as possible. That's C, E, B. And then I drew that so badly. Let me try that one more time. Oops. That's F, DC. And I'm going to set up my statement reason true. Just like with the other ones, I'm going to just not write the givens down for the purposes of this video. Okay. BE is perpendicular to CED. So it forms right angles. It forms both of these right angles, but this is the one that helps me because it's angle BEC in this triangle over here. And then we have that DF is perpendicular to BFC, so it forms two right angles. But the one that's helpful to me is this one because it's angle DFC in this triangle over here. Let me put that into the proof. Angle CEB and angle CFD are right angles. And that's because perpendicular lines form right angles. And now I can say that angle CEB is congruent to angle CFD because all right angles are congruent. Then they tell us that CE is congruent to CF. It's a little bit hard to see in the original diagram, but if you separate it, in our givens, they already give us a side. So already we have an angle and a side from our givens and from the right angles. When you have overlapping triangles, they usually share something. If you look at the separated triangles, it's easier to see what they share because you can look at the letters and see which letter is the same. If it's one letter the same, it's going to be a shared angle. If it's two letters that are the same, it's going to be a shared side. C is the same, so it's a shared angle. Angle C is congruent to angle C. And that's by the reflexive property. So what we have here is we have angle, side, angle to prove the triangle's congruent. Triangle BEC, sorry, my pen is being weird today, is congruent to triangle CFD. And that's by angle, side, angle. Now, as we discussed in the beginning, now we can CP, BC, and CD, which are the sides that we wanted. Because once the triangles are congruent, their corresponding sides and angles are congruent by CPCTC, corresponding parts of congruent triangles are congruent. And now we can say ABCD is a rhombus, a parallelogram with congruent adjacent sides is a rhombus. That one wasn't too bad. Okay. Next, there's two ways to do this one, so I'm gonna just do it one way and I'll talk about the other way in case somebody did it the other way. So our first goal is to prove that triangle ADE is congruent to triangle BCE. So we're gonna start with that first. Let me make my statement reason chart. And I'm not gonna write the givens, but I'm gonna make a spot for it. So we have an isosceles trapezoid. And one property of isosceles trapezoids is that the legs are congruent. Legs of an isosceles trapezoid are congruent. They also tell us that angle CDE is congruent to angle DCE. And that means that in this triangle over here, DEC, there's two equal angles. And that means the sides across from the angles are congruent. Remember, if you have a triangle with two equal angles, the base angles, the sides opposite are congruent, making it an isosceles triangle. The other way around is true too. If it's an isosceles triangle, the base angles are congruent. If the base angles are congruent, then it's isosceles. So I'm going to put that here. DE is congruent to CE. If two angles in a triangle are congruent, the sides opposite those angles are congruent. And they also tell us that AE is perpendicular to DE and BE is perpendicular to CE. You might think that this is ASS or SSA, which doesn't work. It's ASS backwards. But what we really have here, since we have right triangles, is HL. I have congruent hypotenuses and a pair of congruents. For HL, when I put the right angles in, and I'll show you angle DEA and angle CEB are right angles because perpendicular lines form right angles. So when you're using HL, it doesn't have the name, so you don't need congruent angles, you need right triangles. So instead of saying the right angles are congruent to each other, I'm gonna say triangle DEA and triangle CEB are right triangles as a triangle with a right angle is a right triangle. And now, since we've already established the congruent hypotenuses and a pair of congruent legs, we can say triangle ADE is congruent to triangle BCE by HL. This is not the only way to do it. Another way to do this proof is that another property of isosceles trapezoids is that the base angles are congruent, and you can use subtraction to get this angle, and then you can use either AAS or angle side angle. So as long as you have the information for it in your proof, all of those are options. I just went with HL because we don't really do a lot of HL, so I figured it's good to show HL here. The second part of the proof is to prove that AEB is an isosceles triangle. So once you prove triangles congruent, remember all the corresponding sides and angles are also congruent due to CPCTC. and AE and EB are sides of the triangles that we just proved congruent. So we can say AE is congruent to CB, CPCTC. I'm just going to continue over here. And now we have everything we need to finish up the proof and say triangle AEB is isosceles. And what makes something isosceles is that a triangle with two congruent sides is isosceles. One more proof to go here for this video. So in this video over here, in this question over here, we have a rhombus. And if we look at the proof statement, we're proving SE is congruent to EV. Here's SE and here's EV. So those are sides of these two triangles. So if we can prove those two triangles congruent, we could just CPCTC those sides that we need. Okay, let me write over here, given, and let's get started. One special property of a rhombus is that all the sides are equal. OE is congruent to PE because all sides of a rhombus are congruent. Or you could say consecutive sides or adjacent sides are congruent. All of that's fine. We also have vertical angles. Intersecting lines form congruent vertical angles. And in the givens, they also give us that angle SPR is congruent to angle VOR. And another special property of rhombuses is that opposite angles are congruent, because that's a property of parallelograms. So rhombuses also have it too. That's angle EOR and angle EPR. And I'm just going to write opposite angles of a rhombus are congruent. So if I take angle SPR, this whole angle here, oops, and I subtract off angle EPR, what left over with is this angle right here, angle SPE, which is inside the triangle that I want to prove congruent. And then if I take the other pink angle, angle VOR, and from that subtract off angle EOR, I will be left over with angle VOE, which is the angle that I want inside of the triangle and proving congruent. So the step over here is subtraction. And then over here, we have substitution. And now I have everything I need to say the triangles are congruent. This is going to be angle side angle. So I can say triangle SPE is congruent to triangle VOE by angle side angle. And then I can say that SE is congruent to EV by CPCTC, because those are corresponding sides. Oh, sorry, EV, corresponding sides of the triangles that we just proved congruent.